Hello everyone. In this presentation, we are going to discuss about formulation of admittance matrix. As a mathematical model and solution of electric network, mathematical model of an electric network is the basis of modern power system analysis. Used in the studies of power flow, optimum power flow, fault analysis and contingency analysis. As the power system is the interconnection of many terminals, many networks, many generators, many systems, many loads, maybe many subtransmission networks, many substations. So it is very difficult to analyze on paper. So it is required to make a computer program for this. To make a computer program, so we need to make a mathematical model of this, through which we can calculate power flow and also find what is the maximum power flow is possible. We can have fault analysis and we can study the contingency conditions, etc. So electrical network is constituted by transmission line, transformer, parallel series capacitors and other static elements. From point of view of the electrical theory, no matter how complicated the network is, we can always establish its equivalent circuit and then analyze it according to the AC circuit laws. The electric network is represented by linear lumped parameter model that is suitable for studies at synchronous frequency. Here synchronous frequency would be 50 Hz in India, whereas if you take some other places like USA, it is 60 Hz. For electromagnetic transient analysis, the high frequency phenomena and wave process should be considered. So when you want to formulate the mathematical things, so we require to have equivalent circuits. So we need to find equivalent circuits using distributed parameters. An electric network can always be represented by a nodal admittance matrix or a nodal impedance matrix. So while we are calculating power, active reactive power, we can find using admittance matrix is easier than using nodal impedance matrix. A modern power system usually involves thousands of nodes. The nodal admittance matrix is one of typical power system. It is a large and it is a sparse matrix. The nodal impedance matrix is widely applied in the fault analysis of power system, node equation and loop equation. There are two methods usually employed in analysis of AC circuit. First one is the node voltage method, another is loop current method, or sometimes it is called mesh analysis. Two generators and an equivalent load with 5 nodes and 6 branches whose admittances are Y1, Y2 till Y6, assigning the ground as a reference node, we can write nodal equations according to the Kirchhoff's current law, V1 dot to V5 dot. So this would be the 5 equation, Y4 V2 minus V1 dot plus Y5 V3 dot minus V1 dot minus Y6 V1 equal to 0. So these equations are written for the circuit diagram shown in this figure. So we can see how the nodes are there. So this would be node 1, this is node 2, here you have node 3, node 4 and node 5. So when we are writing equation, we have to assume whichever equation we are writing equation for each node. So when we are considering this node, so we have to write with respect to V2. So here V4, here when we are writing, we have to see the current, whether current is coming or whether it is going. So based on that we'll write the equation. So when you see these equations, we can see, for example, here this equation 1 is written with respect to node 1. So with respect to here, the voltage is V2 minus V1. So this would be voltage. Similarly V3 minus V1. So here reference node is V1, and similarly we are writing other 5 equations. So if you rearrange these equations, it would be in this form. So y4 plus y5 plus y6 into v1 minus y4 v2 minus y5 into v3 equal to 0. So when you rearrange this equation, and this would be the general, if you take any random, so what are the maximum possible values? So it would be a matrix of y11, y12, y13, y14, y1, so on in these 5 equations. So when you compare, you will get y11 as y4 plus y5 plus y6, so on. Similarly, so these are all y11, y22, y33, y44, y55, y. These things are called nodal self admittances, and y12, y13, y23, y24, y35. These things are called mutual admittance matrix between the connected loads. The generalized form of the n node network would be I equal to yv. So where I is a matrix of I1, I2 till In. Similarly, V is matrix of voltage V1, V2 till Vn. And here the Y is known as admittance matrix, which is y11, y12 till y1n, and y21, y22 till y2n, and so on till yn1, yn2 till yn. So this is called admittance matrix, where here I is vector of nodal injection currents and V is vector of nodal voltages. So this is, from above equations we can see A is equal to this matrix. This matrix is called incidence matrix. So here the number of columns are I1, I2, I3, I4, I5 and I6, and rows are V1, V2, V3 till V5. So you can see the element of the incidence matrix is only 0 or 1 or minus 1. There are 5 nodes and 6 branches. Its incidence matrix, a matrix with 5 rows and 6 columns. If branch current flows into the node 0 elements equal to minus 1. If the branch current flows out of the node, the non-zero element equal to minus 1. The position of the non-zero element in the each column denotes the 2 node numbers of the relevant branch. If there are n nodes and b branches in the electric network, the state equation for every branch is I bk equal to y bk into v dot bk, where y bk is admittance of the branch k and I bk dot would be the current flowing into the branch k, and y bk dot is the voltage difference between the branch k whose direction is determined by I bk dot. So if you take those things and if you write equivalent current source, so this would be the equation y bk equal to 1 by z bk and a bk equal to e bk by z bk equal to y bk dot into e dot bk. So this is the equivalent in a pictorial way. So this would be a transformation from voltage to current source, that is IB equal to YB into VB, where IB is a vector of the current in branches and VB is a vector of branch voltage differences, and YB is a diagonal matrix constituted by branch admittances. Using Kirchhoff's current law, the injection current II of node I in electric network can be expressed as follows: II equal to k equal to 1 to b summation AI IBK, where I is 1 to n, where AI is a coefficient, and if branch current IBK direct towards node, then it is minus 1. If branch current IBK direct towards away from the node, then I equal to AIK equal to 1. If branch K does not connect to node, then AIK is 0. It is easy to get the relationship between nodal current vectors I and branch current vector IB as follows: I equal to AIB, where A is incident matrix of the network. Power consumed in the whole network is given by S equal to sigma I equal to B, IBK, VBK, I into VB dot, where the cap IBK and cap IB are conjugate of the corresponding vectors, and star is the scalar product of the two vectors. So this would be the equations. and where finally we can come to equation after simplifying y equal to a yb a transpose, where y is nodal admittance matrix. So thank you.